All right, so we're at the final lesson, lesson number 4 for our kinetics unit. It's going by pretty quick. So this one's reaction mechanisms. So in previous chemistry courses or science courses, reactions are expressed using reaction equations. So like this one here, A2B2 going to 2AB, right? Very simple. The equation gives us information about the reactants and products, but very little information about the process that occurs from the reactant to the product. An equation suggests a one-step process, which in reality is seldom the case. Most reactions involve a series of steps in order to go from our reactants and products. So you can kind of think about it as like you're going on a road trip from Victoria to the Grand Canyon, right? So reactants, Victoria, Grand Canyon is our products, but a lot of stuff happens in between on a road trip, right? You have to go on different ferries, you have to cross the border, you spend the night in Oregon, and then again in California, right? So you're doing a lot of little things, and that's a mechanism. So that's what makes up going from your reactants to your products. So there's different steps that are involved in going from your reactants to your products, or just like in the road trip, going from your where you started your origin to your destination. All right, so let's take for example, right? So we got this equation here, right? Never, don't worry about the products on this, but we can just look at it. It involves 23 reacting particles, right? So all these bonds have to break and then reform, and like a lot of things have to go perfect in order for it to happen in one step, right? So 23 reactant particles, there's a lot of chance that ones are going to hit each other. They're not going to hit the right ones. They're not going to react in one step. So the chance of all these colliding perfectly and taking place in one step, this is almost zero, right? So there's a chance, but it's similar to like putting some yarn and some knitting needles in a bag, shaking it up, and coming out with a nice, perfect Christmas sweater, right? So chances are pretty much zero for this happening in one step. So you're going to have lots of different steps going through this to make this happen. So even a three particle collision, right? You have to have these guys broken up. These guys have to break up perfectly. They have to hit each other in the right time. So it's probably not going to take place in a single step, but 1,000 times less probable than a two particle collision, right? So most reactions, other than two simple particle collisions, like we got Ag plus and Cl minus. So these are like precipitation reactions. So you get these ions coming together. There's a chance that could happen in a single step, right? But you still have the chance of the Ags bumping into each other, or the Cls bumping into each other and not happening. But this is very likely because you have the positive and negative charges that they're going to slap together like a magnet, and they're gonna form the products. So in most reactions, they're going to take place in a series of simple steps, or elementary steps is what they're called in our book, right, and on other textbooks, with each step depending on others before it. All right, so it's kind of like an assembly line where you have to get step one done before you do step two, right? So yeah. All right. So reaction mechanisms, the series or sequence of steps by which a reaction takes place. That's your reaction mechanism. So cannot be determined just by looking at the overall reaction. Deduced through much years of study, up to years. So we're never going to ask you to come up with a reaction mechanism, right? We'll just ask you to interpret it, and we'll talk about that's pretty much what this lesson's all about. All right, so some mechanisms are known, many are yet to be discovered. So they all work the general premise, right? You got A and B reacting together. So these are reactants, and then you produce something C, and then C gets used up, goes with D, and then it produces E. So you have these things that are being produced before that being produced in one step get used up in another step. Those are called intermediates. So you have these things that are depending on the product being produced from things before, and I'll show you an example of reaction mechanism in class. All right, so for the overall reaction, right? So this is 4 HBr plus O2 going H2O and Br2. All right, so this is the overall reaction, reactants and products, just like we've seen before. The three-step mechanism, the term from lots of research, right? This is, and each one's called an elementary process, like just like elementary school is a simple process or a small process, right? So you can think about like that. So small school, elementary, or simple small process. All right, so step one, right? So you got this HBr plus O2 going to HOOBr or Huber. All right, so this is found to be slow, this step. Step two, right? You got this, and then you're producing this over here. So you got this one, HBr, HOOBr, and HOBr. So that's fast. And then we got HBr going to H2O and Br2. And so that's very fast. All right, so we know the overall reaction equations up here, but given the steps, we can find out what the overall equation is. Basically, whatever's on both sides, the left and the right, they are going to cancel each other out. Right, so we see in their first step, we produce Huber here. We got Huber being produced in this first step, Hober being produced in the second step. So they're two Scandinavian brothers or something like that. So we got Huber and Hober being produced and then used up, being produced and used up. So we can see Huber on both sides, so we cancel it out. Hober, right, both sides, and cancel it out. And then we're just going to add up the things on both sides. So we got HBr, HBr, and 2HBr, right? So that's going to make 4 HBr. We can see at the top O2, right? Just one O2 left on the left side there. Left side 2H2O and 2Br2. All right, so that there's an overall reaction. That's how you take each step and then find the overall reaction. We'll do more practice with it later on. So some things to note, I put notes on the other side, but you can mark up your page. So this one over here, the step one, this is found to be slow. So this is called the rate determining step, or our RDS, right? So you can never be faster than your rate determining step. So just like in the assembly line, maybe you're waiting for somebody to do in step one. So step two can't happen until step one is completed, right? Or you have like the three-legged race or something like that, or the five-legged race or something like that, where feet are tied together and you're only as fast as the slowest person. All right, so rate determining step, the slowest step in the mechanism. The overall reaction can never be faster than the rate determining step. The only way to speed up an overall reaction is to speed up the RDS. So by increasing the concentration of the reactant of the RDS. So for example, in the reaction above, in this one here, right, increasing our concentration to HBr or 2 would speed up step one. So this rate determining step, and then the overall rate would increase. All right, so if you sped up a fast rate, right, like in our step 2, added more Huber or Hober, right, it's going to have no effect on the overall rate. You're just making something that's fast already fast. So it's like making the fastest person in the five-legged race faster. It's not going to happen. It's not going to make everybody else faster because you still got that one slow person. All right, so let's do some more practice with these. All right, I encourage you, you can try this, do it, and then find out, try it yourself, and then see how you did when I'm after me. All right, so basically what you want to do, anything that's on both sides, cancel it out, and then add up the stuff on the left and add up the stuff on the right. All right, so I encourage you to try it first and then see how you did. All right. All right, so we got this on the left, AX2 on the right, AX2 on the left. So those guys cancel out. All right, we can see AX on the right here and another AX on the left over there. All right, check it over. Do we see anything else? Oh yeah, so there's another X on the left, and then there's an X on the right. Okay, so we've crossed out everything that we don't have. Add them up. We got two A's, two X's. We got an A2 and an X2 on the right. So there's our overall equation, canceling out the stuff that's on the left and on the right. Okay, next one. So these ones are a little bit more difficult, right? So the following reaction occurs in 3 steps. Determine the missing step in the reaction. So there's different ways to go about this type of problem. Basically, you're going to look in the overall step, right? And you want the stuff that's going to be in the, so I'm going to start it this way. So I'm going to look in the overall step, and I want the stuff on the left side to equal what I have on the left side, stuff on the right side to equal to what I have on the right side. If I have something in our step 1 and 2 that need to be canceled, I'm going to put them on opposite side. So first I'm going to concentrate on what I need to figure out with my left and my right side. All right, so A4 plus, right? There's that. And then we got A4 plus in the final. So 2 A4 pluses, that's good. But I don't see any B pluses on the left. All right, so I'm going to have to add a B plus on the left. All right, so now I'm going to look at the right side. What do I need to add? So A3 plus, right? 2 A3 pluses, so I got that. C3 plus, all right, so I'm missing a B3 plus on the right-hand side. So I'll add my B3 plus on my right-hand side. Now I got to figure out things that are going to cancel out. All right, so I notice a C4 plus on the right here, but there's no C4 plus in the overall equation. So I got to cancel it out on the left over there. Well, I guess I did opposite. C2 plus on the left over here. I got to cancel that out with the C2 plus on the right. And then again, like what I was saying, the C4 plus on the left, and I got to cancel it out for the right. So what you should do after you get these questions done, sub it in there and then cancel it all out. Make sure everything works out, stuff you have on the left side, stuff you have on the right side, and you're good to go. All right, so encourage you to do this one, okay? Try it for yourself, okay? Step 2, just like before, find out what's in the overall equation, what you need, put it on the left. What's in the overall equation on the right, put it there, and then cancel things out how you get it. All right, so I'm not gonna go through this one. I want you to try it. Here is the overall reaction, all right? All right, so let's talk about reaction intermediates. So this is a species atom molecular ion, which is produced in one step and used up in a later step. All right, so we'll talk about catalysts later on, where you have them introduced at the beginning and they go out at the end, but we're talking about intermediates. So I'll tell the difference between those ones later on. So produced on the right, used on the left. All right, so we got Huber here, right? Huber's on the produced on the right and then used on the left. So Huber's one of ours, and we got Hober over here. Hober produced on the right, used on the left. All right, so everything else, our HBRs, or O2s, or waters, or our bromine gases, or Br2s, those are reactants or products. Intermediates appears on the right and then also on the lower left. All right, that's our definition for an intermediate. See it on the right. So Huber and Hober are both our intermediates. All right. So an intermediate doesn't accumulate like a product because as soon as it is formed, it gets used up again like money, right? You get it and then you use it. Intermediates are not necessarily unstable. In other circumstances, they may last for a while. An activated complex is very unstable or short-lived. It doesn't usually obey bonding rules, right? They're non-real bonds in our activated complex. So people sometimes confuse activated complexes with intermediates. Connecting it with the potential energy diagrams. So before in our potential energy diagrams, we just had reactants, right? Or over here, reactants and our products on there. So we can see here, this is three bumps. So it's going to be a 3-step process. And there's our intermediates. So on the peaks of these, we have our activated complex. In the valleys, we're going to have an intermediates. Peaks, activated complex, valleys, intermediates. If you want to see the pictures of the activated complex, which are just mishmash of all the reactant particles, those would be from your textbook. So page 26 or 27 for these ones as you go along. All right, so this one here, we can look at it, right? It is exothermic reaction, right? So we can see products are lower than our reactants on it, right? So we put energy in, right? Activated complex, intermediate. Activated complex, intermediate. Activated complex, products. All right, so 3 steps, 3 bumps. If we had a 4-step one, it'd be 4 bumps. If we had 2-step, it'd be 2 bumps, right? So just the peaks and the valleys help us determine how many steps. And we have our activated complexes and our intermediates. All right. Again, like I said, each bump is a step. The higher the bump, the greater the EA. Therefore, the slower the step, right? So you have to ride your bike up that hill. The bigger the hill, it's going to take you a longer time. So it's going to be the slower the step because you got to break those bonds. The highest bump measured from the reactance level is the RDS, rate determining step. All right, so highest bump, remember to measure it from the reactance level. Activated complex, top of the bumps, intermediates are the valleys, products in the final valley. The EA for the forward overall reaction is a vertical distance from the reactants to the top of the highest bump. So that's our overall EA for the reaction. So here, this is like we can see, it's a three-step endothermic reaction, right? Our overall EA reactance level to the top of the highest bump. If we want to do the EA for the second step, it would be here, the valley, all right, to the top of the bump, right? The EA for the third reaction, for the third step would be here, right, in this valley here to the top of the step. All right. So assume these lines are straight. It's not the best graph, but we'll kind of demonstrate it. So this reactive mechanism, so we'll go through these questions together. So this reactive mechanism, we have 1, 2, 3 bumps, so it's got 3 steps. EA for the overall reaction, go from the reactance level at 50 to the highest bump is 80. So 80 minus 50. So the EA for the overall reaction is going to be 30. All right. The largest bump, step 2, right? Rate determining step. So that's our biggest bump. So that's going to be our rate determining step. Fastest step. It's hard to tell the difference between them. So step 1 or 3 is going to be the fastest step, right? It's not the best graph, but anyways, 1 or 3, right? Fastest step, maybe, yeah, it's not. We should make it more on a test or quiz. It'll be more apparent. Our delta H, or sorry, we're on number 5. So the overall reaction, so reactants are here, products are up there, so it's an endothermic reaction. So delta H is going to be positive. So that's a difference 50 and 70. So it's about positive 20 kilojoules for this. Remember, endothermic is going to be positive, so make sure you put your positive sign there to distinguish it from the negative, right? So delta H for the reverse reaction, going from right to left. So that's going to be your negative 20 kilojoules for that. EA for the reverse reaction. So we got 70 all the way up to 80. So it's about 10 kilojoules for the EA for the reverse reaction. The rate determining step for the reverse reaction is also our step 2. All right, so those are your potential energy diagrams. Get comfortable with these. We'll have more questions on them later. All right, let's go on to catalysts. So catalysts, I'm sure you've come across them before. We all know that they increase the rate of a chemical reaction, right? So you add a catalyst into it, it makes the reaction happen faster. So the analogy we're going to use for this one is to avoid a hill, we build a tunnel. Right, instead of walking all the way up and over top of the hill, we can just go right through the tunnel, make things much easier. Right, it's a lot of work to build that tunnel, but once we got that tunnel built, then everything is much easier. Right. Catalyst is an introduced substance which produces an alternate mechanism with a lower activation energy. That's our definition of a catalyst. You introduce the substance, you add the substance in there, and it's an alternate mechanism with a lower activation energy. Sometimes it's more steps, sometimes it's the same amount of steps. Every type of reaction follows a specific and consistent pathway with a unique activated complex. When catalysts are introduced to the reaction, the pathway changes and a different activated complex is formed with a lower EA, activation energy. Because of the lower activation energy, a higher percentage of collisions are effective, thereby increasing the reaction rate. All right, so sometimes it's adding a reaction intermediate to make things happen faster. Sometimes it's a surface for the reaction to do, and in like the surface, like in like a catalytic converter in the car, is actually prying apart the bonds of something. So it's like a platinum thing for in order to make the reaction happen faster. But we don't have to worry how catalysts work. We just have to know how it influences our potential energy diagrams and how it looks on a mechanism equation. Opposite of that is an inhibitor forms a new activated complex that has a larger activation energy, thereby decreasing the reaction rate. All right, so inhibitor works the opposite way. So catalyst by definition, lower EA, inhibitor higher EA. All right, so we look at this one. So this is uncatalyzed reaction. We talked about this before. So our hydrogen peroxide going to water and oxygen. Maybe I'll do a demo of this in class by adding the catalyst. Maybe you've seen before the elephant toothpaste one. That's a common one with this, where you add dish soap to it and you see it looks like elephant's toothpaste. So with this one, so we have this. So H2O2 plus I minus going to H2O, and then the OI minus, right? So this is our intermediate. So the I minus in the form of Ki is making an intermediate OI, and then the intermediate gets used up in the next one, and then we can see it goes out at the end. So in other reaction equations, maybe you've seen it over top of the arrow. So you'd have Ki or I minus over top of the arrow to show that it's not a reactant, it's not a product, it's a catalyst. Here in this mechanism, we can tell it's a catalyst because it starts at the beginning on the left and gets used on the right. Right, our intermediate, the OI is an intermediate, OI produced on the right, used on the left. So those are the difference between our catalysts on the left, used on the right, intermediates produced on the right, used on the left. All right, but they're not going to be in the overall equation. All right, so those are our catalysts. How it influences the PE diagram, right? So two things we have to know: mechanisms and our PE diagrams. We can see the uncatalyzed route. These are EA, right? Our catalyzed route has a much lower EA, right? And then more steps, right? This one has one bump, this one has two bumps. So it's a catalyzed route for that. Our delta H stays the same. The route, the reactants and products are exactly the same for this, right? The catalyzed route in the reverse reaction, right, is also, the EA is also lower. So for a forward reaction, if a catalyst lowers the EA for the forward reaction, it's also going to lower the EA for the reverse reaction as well. All right, so some notes for catalysts. The energy required is less with the catalyst. If you're not having less EA for the catalyst, it's not a catalyst, right? So more molecules can make it over the barrier, so the reaction speeds up. So it's analogous, or it can be the same as lowering standards for a pass, right? If we put standards down to 30%, then you're going to have more students pass a course, right? You're going to still, so it's just lowering that the standards there. So we'd lower the EA. So catalyzed reactions usually involve more steps, but not always. But its highest EA, the highest bump, is never as high as the uncatalyzed reaction. A catalyst never changes the potential energy of reactants or products. It should be an or, not an of. Only the route between them. There's no change in our delta H. Doesn't change the beginning and end, just how it gets there, right? So it's like the tunnel. So you're not going all the way up and over the mountain. You're going to go through the mountain. Uncatalyzed reaction still continues at its own slow rate. When a catalyst is added, usually insignificant compared to the catalyzed rate, right? So uncatalyzed reaction, it's going to happen over a year for the hydrogen peroxide, whereas the other one will happen in seconds, right? So you still have the one going through the regular route, but it's going to be insignificant, and you're going to get rid of all the reactants before that even happens. All right, so if a catalyst speeds up the forward reaction, it also speeds up or reduce the EA for the reverse reaction. All right, example of potential energy diagram show what the catalyst may change. So again, right, so you have the uncatalyzed route, the big one in the dashed line, right, and the catalyzed route making more steps, and you have different reaction intermediates as you go from your reactants to products. But we can see the highest bump the highest bump of the rate determining step is never as high as the uncatalyzed reaction. All right, so this is just another graph comparing the energies of forward and reverse reactions. So very similar from before. So you got the catalyzed and uncatalyzed. If it lowers the EA in the forward reaction, it's going to lower the EA in the reverse reaction. Delta H stays exactly the same. Excuse me. All right, so that's it for our lesson 4. All right, let me know if you have any problems in class.